Tagadan 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 pam pam tagadan 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 pam pam tagadan 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 pam pam tagadan.
Thank you for joining us for day 2 of the 2-day HPCA AI Advisory Council, Swiss Conference, and HPC XXL User Group. I'm Brian Sparks, Director of Worldwide Operations for the Council, and will be today's moderator. We have a robust agenda for the next 3 hours with great topics and speakers. I encourage everyone to ask questions via the Q&A window, and our presenters will try to answer them after their presentation. This webinar is being recorded, and the sessions and the slides will be available on the Council's conference website over the coming days, as well as our YouTube channel. With that, let me introduce you to Gilad Shainer, Chairman of the HPC AI Advisory Council, and Hussein Haraki, the HPC System Manager at CSCS, to kick off the day. Gentlemen, how are you?
Hey, doing fine, thank you, Brian. Good morning, good afternoon, and good evening. Depends where you're located. Thanks for joining. It's just great to see you again for a second day. Well, I'll start with, a couple of announcements. I mean, the first one is good. There will be no opening session. I mean, there's no presentation during the opening session, and this is good news. The second, actually, it has to do with with the ETH team, the student cluster competition. I mean, decided to join the SC competition. We submitted and waiting now for this, which is also good news. That will take us to SC student cluster competition, doing our best to see how we can do. With that, actually, these are the only 2 announcements, and we'll start with the first talk. Actually, Gilad, he will just tell us a little bit about this nice integration that all is looking for, at least from our side, about cloud and HPC, and benefit from both of them joining these 2, working together to bring innovation to the HPC. Gilad, stage is yours.
Oh, thank you very much. It's definitely great to have a team from ETH or a team from Swiss that will go and participate in the student cluster competition at Supercomputing in November. It's a great competition to prepare the team for the really tough competition that's happened at ISC. So I do put you on a spot here, or try to challenge you that after you take the team to the Supercomputing student cluster competition, also take them and go to the ISC competitions, which actually brings the winning teams from various competitions, right? It brings the winning team from Supercomputing, the winning team from South Africa, winning team from China, winning team from Singapore, and actually it's the master of the competitions. It's the World Cup of competitions. So looking forward, and I hope that we'll see the ETH team also going to ISC in the future.
Thank you, Gilad. I'm going to say 1 sentence more actually to answer. Yes, after SC, we'll be just doing our best to get the team. We have a solid team, and I believe we have even 2 more members than the required number. So I definitely believe that it's going to happen after SC, so for 2022.
Looking forward.
Thank you.
I'm happy to present this morning, or to run the first presentation this morning. Let me share my screen. Here we go. The original plan was to actually have this session presented by 2 speakers. Myself, or I should start with the other one, with Paul Kalija from Cambridge University, and with me as well. Unfortunately, Paul is not able to join today from due to other commitments. So I'll try to also present Paul's side, or the story of Cambridge University as well. So we'll talk about cloud native supercomputing, which is a new concept. It's a new architecture that I'm happy to be part of the development of that, part of creating the architecture or creating the capabilities for something that will be probably something that will form or be the base for future supercomputers. So first, when we look on scientific computing, we're looking on completely new universe in that sense. We're looking on it's not just a single system or one data center that runs simulations there and that's it. When we look today on scientific computing, it actually expands all the way to the edge. The places we source data. And in the places we source data, due to the fact that there is growing amount of data and due to the fact that we want to solve more complex problems, we cannot just send data from all of the sources into that supercomputer in the middle and just do everything there. So we start moving to the edge and start with doing the first analysis actually the edge. So scientific computing started at the edge. The places we source data, we're running the first class simulations. We're doing first analysis of data. Then from that point, there is a need to send the first insights in a secured way, fast way, efficient way into different components. It could be the supercomputer, it could be the storage, it could be appliances. We want to create fast visualization from the supercomputing into workstations. We want to move data from edge computing into different kind of areas. So we're talking about much complex environment that goes from the edge to appliances to storage to the data centers to the supercomputers, and as well we need not just to be able to analyze fast and move fast, but also to secure that information. And therefore, there is new architectures that are being developed in order to fulfill the new demand of scientific computing. Now, if we go back several years, maybe more than several years, the traditional data center long time ago was actually built from let's say server storage, and then the network in the middle. The task of that network in the middle was just to move data from one side to another side. The CPUs or the compute elements were active in managing the network data transfer, in managing the ability to move data between processes. And in those areas, the CPU time was actually split more or less 50-50, 50% running the applications, 50% managing the infrastructures and the data transfer and so forth. Ping latencies were in the range of 10 microseconds, and the HPC framework latency, which are the more complex operations, that latency was really, really high. And then RDMA was created. And when RDMA was created and transport offload were created, that meant that now the CPU overhead of managing the network was reduced to almost zero. And now you can get 90, 95%, 97% of the CPU cycles to be dedicated to the applications, and it doesn't need to actually manage the network. RDMA also enabled to move data directly to user spaces, which means ping latencies become in a range of a microseconds, but still the more complex operations, the collective operations, for example, their latency was high because they were continue running on the host or running on a CPU. Now, RDMA today has evolved to serve multiple needs. Obviously, RDMA to move data from CPU memory to CPU memory, remote CPU memory to remote CPU memory, remote GPU memory to remote GPU memory, storage to GPU memory, and so forth. And one example is the GPU direct RDMA, which is moving data from GPU memory directly to GPU memory, bypassing the CPU. So the CPU doesn't need to be on the data path anymore. That helped to reduce latencies by 10x. And I believe that Professor D.K. Panda did present yesterday the latest results around the GPU direct RDMA. And from almost 20% microseconds, went down to, if I remember correctly, 1.85 microseconds. Getting to same latencies as host to host, or host memory to host memory. On the other side, bandwidth throughput went up as well. Bidirectional bandwidth or unidirectional bandwidth increases in around 10x in an average. So this is example of the importance of RDMA. And today RDMA is the de facto technology for moving data from one side to another side. It's critical for storage, critical for moving big chunks of data and so forth. Now, after that, we actually moved to the next level. And the next level was creating in-network computing network devices, or network devices that includes in-network computing engines. The motivation behind that transition was to enable or move computing closer to the data instead of moving data to the compute. And by moving compute next to the data, obviously you can analyze things faster, you can handle growing amount of data and actually increase application performance and overcome bottlenecks. That happens because the only place for running data algorithm was the endpoint. So we're seeing computing engines being added to networking devices, to network adapters, network switches, and transferring the network to be a distributed compute service in that sense. And those engines enable us now to look or take a holistic view on the application algorithms and run those algorithms in the more ideal place versus to be forced to run them on the host. And there is multiple examples of engines or in-network computing engines that when placing them on the network, you can actually achieve great performance increase, which you cannot do if you would continue doing the same algorithms on the endpoint. One example, it's a technology called SHARP, which is enabling to do data reductions on the network, moving the data reduction protocol to be executed on the switch fabric instead of doing that on the host. The next few slides will demonstrate why this is, or the network is, the ideal place for those or this data reductions algorithm to run on. Other examples are all-to-all engines. And MPI all-to-all engines placed on the network device can dramatically increase small message all-to-all bandwidth, for example. Something that is really limited if you're running all-to-all on the host, on the CPU side. Another example is MPI tag matching. So MPI tag matching is a element that is being executed on the CPU for every incoming MPI message. So every MPI message that gets to the CPU, gets to the node, create actually an interrupt. The CPU needs to look on the posted buffers and the tag that comes on the message, do the matching, and if there is a match, to copy the data to the buffer. Or if there is no match, you need to deal with unexpected message. By taking that tag matching protocol and execute it on the network, it means that the CPU does not need to be interrupted for every incoming MPI message. It means that instead of having the list, or it means that the list of posted buffer will be exposed to the network, and the network can look on that list, do the match, and if there is a match, actually to write the data directly to the user space. So there is no interrupt to the CPU can continue doing the work, which means you achieve great overlapping and reduce latencies for tag matchings. Even more, or even further than that, if you have the tag matching element on the network, you can actually migrate the entire MPI rendezvous protocol to be handled by the network. So if there is a match, and we're talking about the rendezvous protocol, then the network can go to the other side, do the read of the data, and then write it back to the right buffer. So you can migrate a big chunk of the MPI work, eliminate CPU interrupt, reducing latencies, and enabling overlapping between compute and communication. So the first example that I used is data reductions. And to illustrate why a data reduction protocol, the ideal place for data reduction protocol is the network, we can take an example of a three-level factory where we have 8 nodes in this case and three tiers of switches. When running a reduction operations on the endpoint on the CPU, there are different kind of algorithms that implement that over the network, but one of them is recursive doubling in this case. And for doing that, you actually need to run 3 phases of operations just for doing a data reduction algorithm or execute data reduction algorithm. In the first phase, all pairs of processes, or let's make it simple, all pair of nodes will need to send data between themselves. So after phase 1, node number 1 will have the data from node number 2, node number 2 will have the data from node number 1. So both of those 2 nodes have the copy of the data from both nodes. Same for 3 and 4, 5 and 6, and 7 and 8. After we finish phase 1, we're now moving to phase 2, where 1 will exchange data with node number 3, and node number 2 will exchange data with node number 4. So by the end of this phase, node number 1 will have copies of node number 2, 3, and 4, and of course itself. And after second phase is over, we'll need to go to the third phase, where node number 1 will exchange data with node number 5, node number 2 will exchange data with node number 6, and so forth. And by the end of the third phase, now every node has a copy of the data from all other nodes, and we are over with the data aggregation process. On the other side, if we are moving the responsibility of doing the data reduction to the switch network, in this case, all of the nodes will need to send data to the switches. The first tier of switches will do the data reductions among the nodes that are connected to that switch. So for example, node number 1, node number 2 send data to the switch does the aggregation. The same happen in the same time all other nodes. Then the switch continue and progress the data to the second tier of switches, which we do the aggregation among the data that comes from the first tier of switches, send it to the third switch. The third level switch does the aggregation across everything and then broadcast the result back that goes all the way to the nodes. So in this case, you're just doing it in one operations, right? So previously we had 3 phases. Now you have 1 phase. You're sending the data, you're getting it back, full wire speed on the network, and you're done. So it means that first, there is much less data motion. Much less data needs to be sent over the network. The second thing, you do it in a one shot. It's much lower latency. And the more nodes you have, obviously, the latency is going to be increased on the traditional way of running reductions on the host. And if you're increasing the nodes and you're on the same number of switches, there is no increase in latency. So actually, you can get flat latencies. So much lower latency and flat latency, and you don't overload the CPU to be part of this algorithm. So this is a great example of an algorithm that its ideal place to be executed. It's actually not on a CPU, not on a GPU, but actually the switch or the switch fabric. And by implementing compute engines that can do data arithmetics inside of on the data path of the switch fabric, you can achieve great performance and actually overcome performance bottlenecks. So with InNetwork Computing, now we're in the third level of the CPU. Is actually mostly focused on the application. Network transport runs on the network. You have RDMA that bypass the CPU, reduces the ping latency to be very, very low. And now with InNetwork Computing, you can actually reduce the more complex operations of HPC frameworks, or even AI frameworks, can reduce their latency to be small as well. So it's a great thing. Now we're actually going to the next level. So we talked at the beginning on the new world of scientific computing. And in the new world of scientific computing, security becomes more and more important. And last year, as part of the COVID-19 new world scenarios, we saw a lot of cases of users that runs applications on supercomputers that are not supposed to be running there. Users that get access to supercomputers and abuse those supercomputers to run Bitcoin mining and so forth. So this was one example of the need to bring security into supercomputing. The need to start isolating users, trying to protect between users, moving a supercomputing infrastructure from being a shared infrastructure to actually a multi-tenant infrastructure. It's not just security within the data center, it's also security at the edge, and then securing the data moving from the edge all the way to the supercomputer itself. So now security becomes important. And in the same way that in-network computing becomes critical for enhancing application performance and solving a lot of bottlenecks, here also using the network components for security, enable to secure data as it being transferred, but also enabling what we call cloud native supercomputing architecture. And that takes me into the next things that is being developed right now, which will form the main architecture for future supercomputers. So before we talk about what cloud native supercomputing is, we should talk about what a DPU is. And a DPU is a new concept. It's a new concept of a network device. And I'm using examples here from of a product that exists, but it's just an illustration here. A network level, if I go one slide back, a network consists of network adapters, switches, and obviously cables that connect all the components together. The network adapter moves the data from the host into the switch fabric and implements RDMA, implements InNetwork Computing, and so forth. A DPU, which is called data processing unit, includes the same network adapter. All of the IP of that network adapter exists inside of the DPU. Now, what's new in the DPU? So the DPU adds to the network functionality, the full network adapter IP. It also adds multiple of compute engines next to that. In the case here, it's multiple ARM cores, but it's multiple compute engines, acceleration engines, memory interfaces. Now there is a memory on the network adapter. So it's actually change or migrate the network adapter to becomes a data center on a chip or a system on a chip. And that DPU can continue and run the same network functions that exist on a network adapter, but it brings programmable computing capabilities into the device. Now you can ask, what's the difference between in-network computing and programmable computing? The difference is when we talked about in-network computing previously, we meant compute engines that are dedicated to run something very specific, meaning these are pre-configured engines. For example, Sharp, it's an engine that does data reductions. It doesn't do anything else. It just do data reductions. MPI tag matching engines just do MPI tag matching. It doesn't do anything else. So those are the in-network computing programmable, pre-configured engines. Here we're talking about programmable engines. It means you have ARM cores that running Linux. So the network adapter replaced by the DPU actually becomes network adapter that it's also a Linux machine. It's a computer. It's actually a computer that now sits in front of the computer. It's a Linux machine that now sits in front of that Linux machine. And that DPU can also connect it through BMCs to the motherboard, which means that that DPU now can load operating systems. It can clean residual data from different jobs and things of that sort. So the DPU actually enable us to migrate a supercomputer or data center to a cloud native supercomputing or to a secure data center. And the way that it works, it's the following. A traditional data center runs everything on a CPU in that sense, or everything on the host. Meaning the applications running on the host, all the infrastructure workloads, the management of the infrastructure, the isolation, security if you're implementing that, the file system, cluster file system, network file system, everything is managed on the host. Everything is managed on the CPU. Now, when we build a supercomputer, the most important thing is performance. And therefore, starting to bring security and trying to isolate between users and increasing the infrastructure workloads means that we're going to lose performance. And that's why you don't really see security in supercomputers. You actually trust your users. So you give them access to the job scheduler, to the end nodes, they're putting the jobs the job scheduler is running the jobs on the system. You actually trust the users, right? You can give them a list of do's and do nots, but you trust your users. There is no actually full isolations. There is no performance isolations, obviously. So one job or one user can take more performance from a storage access from a shared resource, for example, and starve other jobs, other users, for example. Now, when we bring the DPU into this story, now we have an extra computer in front of the computer. We have a Linux machine, a new Linux machine, which is actually a trusted Linux machine. The CPU is untrusted. It sits in an untrusted domain because it's the same domain that runs the applications. It's the same domain that hosts the users. The DPU sits in a trusted domain. It does not host the users. And you can actually completely manage that separately. So now, with that new Linux machine, you can migrate the infrastructure workloads. You can bring security and isolations. You can bring multi-tenancy support into a supercomputer the same way that you have it on the public clouds, which invest so many in security and job isolations, because if you don't have job isolations in those public clouds, you're not going to run anything there. So you can bring the same cloud services, the same isolations, the same security, run them on the DPU and not increasing any overhead on the system. You can also migrate file system and file system management and do the management on the DPU device. So the entire infrastructure workload, which is probably one of the fastest growing workloads in complexity, definitely because of security, you can actually move the entire workload and run them on the DPU. And it's not just that, because now you have also programmable engines, which means you can further migrate algorithms that could run better on the new Linux machine, which is closer to the data, and essentially creating a new hybrid model. Hybrid model of a CPU, GPU, and a DPU, where you can start splitting algorithm across those three components, as well utilizing the in-network computing engines that are spread across the network. So we're moving to a new architecture which enables security, enables to move away all of the infrastructure management from the CPU, and move us to a new kind of hybrid models for running algorithms. So on the security side of things, by moving the security or actually bringing the security ownership onto the DPU, we can move the supercomputers towards a zero trust architecture. It means that the job or the user is locked inside the host. Everything that's outside of the host is controlled by the DPU. So you can do job isolations or user isolations. You can do performance isolations as well. The storage is storage management. It's also being migrated into the DPU. So now the process actually mounts storage on the DPU. And the DPU is the device that mounts storage on the real storage. So now the DPU can control if a job can access specific storage or cannot access specific storage. So you bring security in that part as well. The DPU connected to the BMC can load clean operating systems between jobs, delete residual information, re-provision what's needed to re-provisions, and actually bring the full security between tenants. So now you don't need to trust the users anymore. Actually, they can come in and you can control or isolate between all of the jobs running there. The technology that is being developed, can handle tens of thousands of concurrent isolated users on a single subnet, which is probably more than what is enough or what is needed for supercomputing infrastructures. It also brings the ability to start dealing with SLAs for different kind of users that get access to a supercomputing infrastructure. So this is one side. So now we bring security for the first time, actually bring security, the same as you have it in public clouds. You can do it on a supercomputer, but maintaining the bare metal performance. So maintaining bare metal performance and having full isolation, it actually comes together for the first time in the new architecture of cloud native supercomputing. Now, the other part is obviously now we can move to a hybrid model, a new hybrid model, not just the hybrid model of a CPU and a GPU, but now we have a hybrid model of a CPU, GPU, and a DPU. And we can use that DPU to do or run different kind of algorithms. And we are learning about new ideas every day, I would say. One of the first concepts that Professor D.K. Panda presented yesterday, one example of that is using the DPU to run non-blocking operations, running MPI non-blocking operations. So non-blocking operations in MPI exist for a long time, but running non-blocking operations on a CPU actually increase over it, because the whole idea of running non-blocking operations is to run that operation on something else than a CPU. So if you have just a CPU, there is no reasons to use non-blocking operations. But now, when you have a place where you can migrate those operations, such as the DPU, you can actually utilize non-blocking operations and move to start using non-blocking operations, because you're going to get performance benefit here. So this is one example. So migrating non-blocking operations of MPI into the DPU, into the Linux machines that exist on the network adapter. You can do interesting things with active messages. So the DPU can get the active message, and now it can do multiple operations based on that message without interrupting the CPU and things of that sort. You can migrate the MPI progression engines. You can do the MPI progressions on the DPU. You can do other things. You can do compressions, decompressions. You can think about different kinds of algorithms that now you can split between the parallel engines, the serial engines, and now the DPU engines, or the data engines, and move towards a hybrid infrastructure. So you can have the users actually have another system, another machine, another server in the infrastructure, another server that they can do interesting things with. So one of the development that is happening, one of the developments on the DPU that is happening, it's as I mentioned before, it's migrating the non-blocking operations into the DPU. The way that it was designed is that there are processes running on a DPU, processes that are called DPU workers. Those processes can receive metadata information from the host processes. which includes a data location, permissions, and what's needed to be done. And from that point, the DPU processes can run operations of local RDMA reads, remote RDMA writes, and perform the entire operations completely bypassing the CPU. So with this capability, you can migrate the non-blocking operations and move them from being executed on the CPU to be executed on the DPU. So by doing that, and this is an example for the performance results, by pipelining all-to-all operations, or by running the non-blocking all-to-all operations, and running all-to-all on the DPU, instead of doing that on a CPU, we're moving from 0% overlapping, nearly 0% overlapping, to 100% overlapping. So that's obvious, right? So CPUs continue to do in the compute. We're running non-blocking all-to-all operations. That operation is runs on the DPU. So now you can go to 100% overlapping. Now, the interesting part is what that can impact on an application performance. And one example is the three-dimensional FFT. The three-dimensional FFT was written in a way to use, or the three-dimensional FFT is using the all-to-all operations as part of running the FFT. So we took the three-dimensional FFT and modified that from using blocking all-to-all operations to use non-blocking all-to-all operations. And after doing that, the team of DK Panda and Excalibur Solutions run the modified three-dimensional FFT on a 32-node cluster with the DPUs, leveraging the hybrid model of the CPU and the DPU here in this case. The result was almost 40% performance improvement for FFT. And we saw that on some specific grid sizes. Overall, when we're looking on different kind of grid sizes, it's a 1.3x performance improvement. So moving or adding DPUs into a supercomputing infrastructure enables to migrate infrastructure workloads, which are increasing in complexity, from the CPU to the DPU. You can actually save hundreds of x86 cores by actually doing the infrastructure workloads on the DPU. You can create a new infrastructure of a cloud-native supercomputing, which means that you can bring cloud services, the security services, the multi-tenancy services, and run them on supercomputers using the DPUs without impacting the performance. So it enable us to achieve bare metal performance with security. And the third one is now we can further accelerate applications by using the new hybrid model of a CPU, GPU, and a DPU, and using the DPU to run the non-blocking operations. And the 1.3x, or in some cases almost 1.4x of performance improvement for the three-dimensional FFT, it's a great example for that. So in Cambridge, working with University of Cambridge, and University of Cambridge is known to be build leading HPC systems over the years. They started before Hussein was born, and in 2006 they built a system that now probably can our cell phones are faster than that. And this year they're actually building a system which is it's part of a 10 petaflop of a system, which part of that system it's actually the world first academic cloud native supercomputers. It's the world first supercomputer that includes the DPUs to form a cloud native supercomputing infrastructure. So the system which you see there on the right bottom side, the Q1 2021 upgrade, is a system that is deployed that includes two aspects. There are Intel CPUs, and I think there is AMD CPUs, and there are NVIDIA GPUs there. And the 4 petaflop system there, which included GPU, is connected through with DPUs and an InfiniBand HDR network to form the world's first cloud-native supercomputer. On that system, University of Cambridge is looking to run different kind of cases, which were identified as something that would be a great start to use the first cloud-native supercomputer for. The first case is obviously to enable better collaborations with medical platforms or medical companies. As we all know, there is a great need from the medical industry to leverage the computing capabilities of supercomputers in order to solve problems that they want to solve. The main issue is obviously they need to protect the data. We're talking about personal information here. And therefore, they need a way to run on a system that has security inside, that has multi-tenant isolations. And by leveraging the cloud-native supercomputer or cloud-native supercomputer, which does brings the multi-tenancy into supercomputing, now they can actually start using supercomputings in a much better way. So one of the use cases for the new supercomputer is to work with the medical entities in the UK and actually have them be able to use the system in the University of Cambridge. The second use case is around storage. And DPUs actually enables to accelerate storage in multiple ways. It enables to accelerate NVMe fabrics. And accelerating NVMe fabrics can be done by actually having the DPU manage NVMe fabrics while the jobs running on the DPU assumes that there is an unlimited local NVMe storage. DPUs can or are being added to the storage servers to accelerate NVMe fabrics, and DPU sits on the client on a compute server and able to migrate the file system, network file system, or cluster file system to run actually on the DPU. As a note, a couple of weeks ago, there was an interesting presentation by Data Direct Network that started talking about their usage of DPUs, both on the server storage and on the client, on the compute server, as part of this process. So the second use case is obviously around storage and accelerating NVMe and so forth can impact great I/O problems across multiple disciplines. And the third use case of University of Cambridge is obviously the performance accelerations is what I demonstrate with the FFT, with the ability to increase FFT performance. And FFT is being used in multiple applications and across different kind of science domains. So that enables to accelerate MPI or support MPI non-blocking operations with that improved performance of applications and improving the capabilities of that system. So this is being brought up, and another thing that is being developed as part of enabling an easier usage of DPUs, because DPUs now provide services of storage, security services, networking services, HPC framework services. You have now services exposed by the DPU to the applications running on top of that. The UCF consortium, which manages multiple projects, some of them are projects that are heavily used by many institutes around the world. One example is UCX, which is an open source library for point-to-point communications that is being used by probably all MPIs across the world, used by deep learning frameworks and so forth. There is the UCC project, which is an open source collective operations project that is being developed. Another project is called OpenSNAPI, Open Smart Network API, which builds or creates API that expose the capabilities of the DPUs as services to the applications running on top. I'm happy that we have Gil presenting later today on OpenSnappy. So he will give, he will give information about OpenSnappy, the open source development. And I do encourage you, go in and check the UCF website. I think Gil probably going to have that website listed on his slides.
I'll provide a pointer and remind everyone. So if you don't join now, I'll remind you in about an hour. So
okay, cool. So there is multiple projects done by the UCF, by the way. So there is UCX, UCC, OpenSnappy. OpenSnappy expose the services of the DPU in easier way, in a standard way, to applications running on top of that. There are other projects, by the way, of UCF. There is another project that's called HPCA, which is an effort to build a benchmark suite to be able to measure computing on the network. We have HPCC, we have HPCG, but there is no real good benchmarking suite to measure computing on the network, and that's the effort under HPCA. So I do encourage you to check out UCF. You can join UCF as an individual. You can join UCF as an organization and participate in the different working group developing those different open source elements. So I think we're well, in the world of HPC, you're always in an exciting environment. And the development towards the next generation of supercomputing architecture, the cloud-native supercomputing, which keeps the maintain bare metal performance, enabling us to cope with the infrastructure workloads, and bring security is a great thing. And one side note. When we talk about supercomputing, typically there are a lot of discussions about applications and the science that it's driving and so forth. The infrastructure workload becomes more and more complex, dramatically more complex, and definitely as we're seeing more and more security requirements coming into supercomputing, that workload complexity is growing exponentially. So we need to be able to deal with that, and actually the DPUs are the ones that can solve the complexity problem of the infrastructure workloads by migrating or running them on the DPU, and also by introducing dedicated engines for these infrastructure workloads. Dedicated engines that can encrypt data at rest or encrypt data in motion, and so forth. So it's exciting times as always in the world of HPC, moving towards the cloud-native supercomputing, and I'm lucky to be part of the UCF consortium as well, and seeing how the development of those open source projects helps in many aspects of our area. So with that, I want to thank you for listening. Let me stop sharing.
Thanks, Gilad. We do have one question related to the DPU SDK. If there is one now, or if that's going to be from UCF as part of like OpenSnappy, or do you expect to see some standardization for these?
Yeah, so there will be multiple, I think multiple options here, and definitely standardization around that. For DPUs, for example, there is a SDK that is called Doka, that is being developed by NVIDIA in one example. So as there is a CUDA for GPUs, there is Doka for DPUs that enables those services. OpenSnappy, it's an open source standardization effort to enable simple programming of DPUs. So yes, you will see open source solutions and vendor specific solution and so forth that brings you the full SDK to use for the DPUs. One more thing, to start with the DPUs, you actually don't need any SDK in that sense. Meaning the DPU is actually a computer. It's a computer that sits in a computer, which you can actually simple SSH to it. You can actually SSH to it. It runs Linux operating systems, and now you have a field of opportunities. So first, you don't need the SDK to start. The second, there are open source SDKs, and there are vendor specific SDKs that are being created. And those SDKs obviously will guarantee that what you run on one generation of DPU will run on next generation and so forth.
Okay, I have a question, Gilad, actually two questions. The first one is the penalty that the PDU could bring. We rely a lot on power, and power is essential for HPC. So what's the penalty from deploying a DPU at the top of computer? That's one. The second part has to do with the software stack that comes with a DPU. I mean, do you have any standard, let's say, a stack that deals with specific cases? For instance, if I take the storage, you say, okay, I will be delivering with the DPU a stack for the storage that will help you to have a standard storage software stack, and you have the possibility to customize it based on your environment. I would just take an example, metadata calculation, offloading it from a storage box to the DPU, or could be for the networking, analyzing logs, or could be for whatever. Do you have any kind of these standards that could help a customer deploying it and modifying it with time? Thank you.
Yeah, no, it's a good question. So the first question, the DPUs that you see in the market are leveraging ARM CPUs there, and ARMs are known as more energy efficient devices. A DPU consumes, I'd say, I don't know, probably 60, 70 watts in a sense. And when you look on a DPU that can replace, for infrastructure workloads, because it has the engines there that can replace 300 x86 cores, you actually save energy by using the DPUs actually in migrating the infrastructure workloads around the DPU. The thing is that you want to become more efficient. And by migrating the infrastructure workloads into the DPU, you actually save energy, completely saves energy from that perspective. So that's one thing. On the second thing, yes, there is a lot of effort to create standard interfaces that expose the services. So OpenSnap is one of those efforts that create standard interfaces. There are other standard interfaces. You can run offed on the DPU, so that means that you have interfaces, the same verbs interfaces and so forth, that gives you access to RDMA operations. Same for storage operations and so forth. Storage companies, DDN is one example, are actually putting their stack on the DPUs. And now they can offer that as a full solution in that sense. But other people that wants to build their own, yes, there are the interfaces. You will see more and more of them being created that gives the standard interfaces into the DPU. So obviously not everything is there in robust and works, because if it would be that case, we wouldn't be talking about that, because that would be history, right? So we're talking about things that coming in the future. And there is a lot of effort around that. There is multiple organizations around the world that participating in the standardization creation. So yes, we'll see that coming. And the one last note, I think it's a call for everyone to actually start looking at DPUs because of those advantages. I truly believe that every new supercomputer being deployed should have at least a small portion of that with DPUs inside. So that can help all the sysadmins to start understanding how to migrate the infrastructure workloads on the DPUs and bringing security. That can enable the applications owners to start moving to the hybrid model and so forth. So you want to have that small infrastructure today to start playing with that, start to get your algorithm folks use the infrastructure folks using that. And in the future, I believe that DPUs will become the default in every server.
bum 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 bum